The strange first creatures that crawled out of the ocean. Imagine a world where fish didn't just swim, they began stepping onto land, shaping the course of life in ways we are only just beginning to understand. Some of these early pioneers had wrists before fingers, lungs before legs, and eyes built for both water and air. How did creatures without modern limbs conquer solid ground? And what secrets do their fossils hold about the leap from water to land? Today's exploration in this video dives into the strange first animals that crawled out of the ocean, revealing the astonishing experiments of evolution that set the stage for all terrestrial life. The line between water and land was once a fluid frontier, and these creatures dared to cross it. Eusthenopteron, the fish with hidden arms. The Devonian world was alive with rivers and shallow seas, where strange creatures moved beneath the surface. Among them swam Eusthenopteron, a lobe-finned fish that lived about 385 million years ago. At first glance, it looked like many other fish of its time, with scales and fins suited for life underwater. Yet inside its body, hidden from view, was a feature that would change the course of life on Earth. What made this animal remarkable was the structure of its fins. Unlike the thin, ray-like fins of most fish, Eusthenopteron's fins held a series of bones arranged in a pattern that resembled the upper arm, forearm, and even parts of a hand. This skeletal layout was not obvious from the outside, but fossils revealed the secret. Within those fins lay the blueprint of limbs, the same basic framework that would one day let animals walk on land. Eusthenopteron was not a land dweller. It swam in freshwater lakes and rivers that cut through what is now Quebec, Canada, where many of its fossils have been found. These waters were crowded with life, from armored fish to early sharks. Eusthenopteron hunted smaller prey, snapping with sharp teeth set in a strong jaw. Its body stretched about a meter long, making it a capable predator in its environment. The discovery of its fossils in the 19th century puzzled researchers. At first, Eusthenopteron seemed like a typical prehistoric fish. Over time, though, paleontologists noticed its bones told a more complex story. When the fins were studied closely, the inner arrangement matched the pattern seen in the limbs of tetrapods, the four-limbed animals that would later walk on land. This connection earned it the nickname the Prince of Paleontology, a title given for its central role in understanding the fish-to-tetrapod transition. To imagine how these hidden bones functioned, picture a fish pushing along the bottom of a shallow stream. The sturdy, lobe-like fins could brace against the ground, allowing Eusthenopteron to maneuver in ways ray-finned fish could not. While it did not crawl onto land, this extra strength may have helped it explore weedy shallows, chase prey into tight spaces, or rise closer to the surface when oxygen levels dropped in the water. The Devonian period, often called the Age of Fishes, was a time of great experimentation in body design. Different groups were trying new strategies for survival, from armored defenses to specialized jaws. Eusthenopteron stood out because its anatomy seemed to point towards something new, though no creature could have known where that path would lead. What began as an adaptation for moving in shallow water would, in distant descendants, open the door to life beyond the sea. Researchers have spent decades debating exactly where Eusthenopteron fits in the family tree. It is not a direct ancestor of all land animals, but it belongs to a close branch of the group that gave rise to tetrapods. This means it offers a snapshot of what fish were like just before the great leap toward land. Each fossil adds another piece to the puzzle, helping scientists trace the gradual shift from fins to limbs. The fossils themselves are remarkably detailed. Preserved in ancient sediments, they show the arrangement of bones with clarity. The humerus, radius, and ulna can all be identified within the fin, echoing the bones in a human arm. Beyond that, smaller bones suggest the early beginnings of wrist and finger structures. Though they were not yet suited for walking, the fact that such familiar patterns exist in a fish more than 300 million years old is one of the most striking revelations of paleontology. Studying Eusthenopteron also sheds light on how evolution works. Big changes are not always sudden leaps. Instead, small shifts in anatomy can accumulate over millions of years, eventually producing something entirely new. In this case, bones that once helped a fish stabilize itself in shallow water became the foundation for crawling, climbing, and walking in later animals. The environment played a role as well. Freshwater habitats often experience fluctuations in oxygen, making it useful for creatures to move closer to the surface. Shallow channels and swampy margins demanded flexibility, rewarding those who could maneuver more effectively. Eusthenopteron, with its hidden arms, was well adapted to these conditions, giving it a survival advantage that set the stage for future evolutionary steps. While Eusthenopteron itself remained bound to water, its body carried the silent promise of land. It never walked across mudflats or breathed air in forests, but within its skeleton lay the architecture that would one day let others do so. That silent promise is what makes it so strange and so vital in the story of life. Even now, when scientists look at the bones of Eusthenopteron, they see not just a fish but a doorway, hinting at the extraordinary creatures waiting to emerge from the ocean after it. Panderichthys, the flat-headed shallow hunter. Shadows drifted across a quiet lagoon over 380 million years ago, where the water was shallow enough for sunlight to reach the muddy bottom. In this world, hidden beneath the still surface, moved a creature that did not look like the common fish of the open sea. Its head was wide and flat, its body stretched long and low, shaped more like something that might rest on land than dart through waves. This was Panderichthys, a hunter designed for a borderland between water and earth. The first hints of this animal's existence came not from shimmering seas, but from layers of rock in Latvia. Fossils unearthed there revealed a skull unlike that of most ancient fishes. Instead of a rounded head suited for fast swimming, the bones were pressed flat, almost crocodile-like, with eyes perched on top. That arrangement told scientists something remarkable. This was a creature built for looking upward from below, a patient predator lurking in the shallows. Many fish of the Devonian seas thrived with narrow heads and streamlined forms that let them chase prey in deeper waters. Panderichthys chose a different path, hugging the bottom and waiting. Its flat skull and elevated eyes worked together to scan the surface above, giving it an advantage in ambushing creatures that ventured too close to the muddy edge. This strategy hints at an early shift toward environments where land and water met. Close study of the fossils revealed more than just a distinctive head. The fins of Panderichthys carried bones arranged in a way that seemed to echo the beginnings of arms and legs. They were not true limbs, but their structure suggested that the scaffolding for shoulders, elbows, and wrists was already forming within the fins. This detail placed the animal in a critical position within the story of transition, more advanced than earlier fishes, yet not fully a landwalker. Shallow lagoons and muddy estuaries offered both danger and opportunity. The waters were warmer and often crowded with life, but they could also become unstable, drying out or losing oxygen. Creatures able to rise to the surface for air or to drag themselves through muck had an edge over others. The body of Panderichthys suggests it was beginning to explore these options, adapting to a setting where land was no longer unreachable. The shape of the jaws pointed to a style of hunting different from its deep-water cousins. Instead of swift chases, it likely relied on a quick upward snap, seizing prey that drifted above. In this way, it resembled later ambush predators that waited in silence until the moment to strike arrived. The wide mouth, combined with the flat head, made it a master of stealth in the shallows. Discoveries of Panderichthys fossils in the 20th century reshaped scientific debates about the origins of tetrapods. For a time, Eusthenopteron had been seen as the key transitional fish. Yet the anatomy of Panderichthys offered features even closer to what would appear in the first four-limbed vertebrates. Its shoulder region, skull bones, and fin skeletons formed a bridge that could not be ignored. Each new fossil gave paleontologists a sharper view of the moment when fish began to test the edges of land. One striking feature of its skull was the reduction of certain bones present in earlier fishes, but absent in true tetrapods. This hinted at a reorganization of the head, a step that would eventually allow for neck mobility in land animals. Although Panderichthys still lacked a neck, the groundwork was being set. It stood at a threshold where evolution was rearranging the architecture of the skull to fit new environments. Shifting tides, drying pools, and fluctuating oxygen would have forced it to cope in ways that demanded more than just gills. Evidence suggests that it may have been capable of limited air breathing, using structures in its head to gulp at the surface. If true, this ability would have given it a vital advantage in unstable waters, pointing the way toward later creatures that carried lungs onto land. While Panderichthys never crawled onto the shore in the way its descendants did, it carried the blueprint of future limbs and the hunting style of a shallow predator. Its life tells us that the transition from water to land was not a single leap, but a series of experiments played out in lagoons and river mouths. It was here, in these uncertain margins, that bodies began to change in preparation for a world beyond the waves. With its flat head, hidden limbs, and shallow water cunning, Panderichthys marked a chapter where evolution was testing forms that blurred the boundary between swimming and walking. And from that blurred boundary, stranger shapes would soon emerge, carrying the story closer to the first true steps on land. Tiktaalik, the fishapod with wrists. The discovery began in the frozen silence of Ellesmere Island in Canada in 2004, when a team of paleontologists uncovered a fossil that would change how we picture the leap from water to land. Lying in the layered rocks was a creature that was neither fully fish nor fully tetrapod, yet it carried pieces of both worlds in its skeleton. The scientists gave it the name Tiktaalik, borrowed from the local Inuktitut language, where it means large freshwater fish. When researchers lifted the fossil from its stony bed, they saw a skull that was flat and broad, with eyes set high on top. It resembled a crocodile more than a common fish, suggesting it had spent its life peering upward from shallow waters. Inside those fins lay a structure that stunned the scientific world. The bones arranged within them resembled a shoulder, an elbow, and even a wrist. These were not true arms and legs, but they allowed the fins to bend and press against the ground beneath the water. This meant Tiktaalik could prop itself up in a way no earlier fish had managed, lifting part of its body to hunt or to gulp air more effectively. For the first time, the basic architecture of a limb was visible in a fish. The rocks where Tiktaalik was found dated back about 375 million years, placing it in the late Devonian period. Insects may have crawled across the damp soil. Shallow rivers and swamps offered new opportunities for predators willing to exploit them. The body of Tiktaalik seemed perfectly suited for these habitats, lying low and powerful in the water, while prepared to venture where other fish could not. Its neck was another surprise. Most fish have heads fused directly to their shoulders, limiting how they can move. Tiktaalik, however, had a separate neck joint, allowing it to turn its head independently of its body. This simple shift was enormous, for it gave the animal freedom to hunt in ways impossible for earlier fishes. By moving its head from side to side, it could strike more precisely at prey near the surface or hidden in reeds. The skull also revealed hints of lungs working alongside gills. Openings at the top of its head suggested that Tiktaalik could draw in air when needed. In the unstable shallows of the Devonian, where oxygen levels often dropped, this ability would have given it an edge. It could breathe in two ways, straddling the line between fish that relied solely on water and the first creatures that would soon depend on air. Fossils suggest Tiktaalik could grow up to 9 feet long, making it a dominant hunter in its environment. With a wide mouth and sharp teeth, it likely preyed on smaller fish and creatures near the water's edge. Its strength, combined with the ability to push itself up with its fins, meant it could explore areas unreachable by less adaptable species. The name fishapod became a fitting shorthand for what Tiktaalik represented. It was not simply another fish with odd bones, but a vivid demonstration of how evolution stitches new forms from old ones. It displayed the beginning of limbs, the rise of a neck, and the dual ability to breathe both in water and at the surface. Each of these features hinted at the lives of animals that would one day leave the water behind. For paleontologists, the fossil also solved a mystery. Before its discovery, there had been a gap in the record between lobe-finned fishes like Panderichthys and the earliest true tetrapods such as Acanthostega. Tiktaalik fell directly in that gap, carrying traits of both. It provided a missing chapter in the story, showing not only that the transition happened, but how it unfolded step by step in anatomy. The location of its discovery mattered as much as the fossil itself. The rocks of Ellesmere Island were once part of an ancient floodplain, a warm and swampy landscape despite today's icy climate. This setting explained why a creature like Tiktaalik could thrive, patrolling slow-moving waters, breathing air when needed, and anchoring itself against soft mud with its sturdy fins. Wrists suggested the testing of weight-bearing, A neck opened the door to new hunting strategies, and lungs hinted at survival beyond the water's edge. Yet it remained a creature of two realms, not quite abandoning its origins, but carrying within it the framework for future explorers of the land. From the stones of the Arctic, this fishapod emerged as a symbol of change, hinting at the creatures still to come that would test the strength of limbs on land for the very first time. Ventistega, the humble early tetrapod. The remains of Ventistega were first uncovered in the late 1980 seconds from rocks in Latvia, a country along the Baltic Sea. There were fragments of skulls, pieces of jaws, and scattered vertebrae. Yet within these modest remains lay a crucial story, one that showed how fragile steps toward land were being tested in unexpected ways. The skull fragments gave the first hints of what this animal looked like. When paleontologists carefully studied the pieces, they found a head shape that resembled that of early tetrapods more than that of fish. The jaws bore teeth of two different sizes, with small rows set beside larger fangs, a pattern seen in creatures that had already begun moving away from purely aquatic lives. One striking detail was the lower jaw. The bones were long and strong, suggesting that this animal could snap at prey with surprising force. Tiny sensory canals ran along the jawline, evidence that Ventistega could detect movement in water the way many fish do. The fossil record places Ventistega about 365 million years ago, during the Devonian period. By this time, the planet was rich with shallow rivers, lakes, and swampy regions filled with vegetation. The environment was unstable, often drying or flooding with changing conditions. Animals that could move between water and land had an advantage, and Ventistega fit into this setting as an early experiment in survival at the edge of two habitats. Unlike Tiktaalik, with its sturdy wrists, Ventistega was less advanced in limb design. The preserved bones suggest it still depended heavily on swimming, and its legs were not yet strong enough to hold its weight on land for long. Its body form may have resembled a flattened salamander, sliding through shallow waters, but its skeleton reveals it was not yet fully suited for walking. This makes it humble compared to the bold features of other transitional animals, yet important in showing the diversity of evolutionary paths. Its shoulder and hip structures provided another clue. These bones hinted at joints capable of more motion than fish, even if they could not yet manage true steps. Such changes revealed the gradual pace of adaptation. Evolution was not a clean line from one form to another, but a branching of different attempts, some leading to land dwellers, others fading away. Ventistega was one such attempt, a quiet marker in the Great Transition. The teeth provided further insight into its habits. Their arrangement suggests it may have fed on small fish, crustaceans, or soft-bodied animals living in shallow waters. The ability to grasp and pierce different kinds of prey showed that Ventistega was flexible in its diet. For paleontologists, the importance of Ventistega came not from a single striking feature, but from its overall mosaic of traits. Its skull leaned toward tetrapods, but its body still swam like a fish. Its limbs suggested beginnings of land movement, but not the full strength required for true walking. The fossil evidence gave a glimpse of a stage where animals were still testing possibilities, where evolution was experimenting with body plans that were not yet perfected. The context of Latvia also matters. During the Devonian, the area was part of a vast floodplain near the equator, warm and covered in waterways. These environments were cradles of innovation, places where fish ventured into weeds and shallows, and where creatures like Ventistega developed features that would one day become common among land vertebrates. The humble fossils found there tied the story of human ancestry not only to Canada or Greenland, but also to the quiet banks of ancient European rivers. Each new fossil adds another piece, hinting at how the animal moved, how it breathed, and how much time it may have spent on land. The gaps remind us that much of evolution's story is still hidden in stone, waiting for discovery. Though not as celebrated as other transitional forms, Ventistega highlights the uneven path of change. It shows that evolution did not move smoothly from water to land in one sweep, but through many small, uncertain steps. Some of those steps, like the ones represented by this animal, may not have led directly to later species, but they reveal the range of possibilities life explored along the way. From the scattered bones of Latvia, this early tetrapod whispers of a time when every new form was an experiment, hinting at the stronger-limbed creatures still to come that would take bolder steps onto land. Elginurpaton, the streamside experiment. The story of Elginurpaton begins not with a complete skeleton, but with scattered fragments of jaw and limb found in the rocks of Scotland. These pieces, pulled from stone that once formed the edge of ancient waterways, hint at a creature both powerful and puzzling. From the beginning, Elginurpaton's remains suggested something unusual, a body built for strength, but not yet fully adapted to life beyond water. The jaws of this animal were long and armed with sharp interlocking teeth. Unlike the rounded mouths of many fish, its bite was designed to seize and hold prey that might otherwise slip away. Each tooth curved slightly backward, ensuring that once something entered its mouth, escape was nearly impossible. This detail paints a picture of a predator lurking near the shallows, ready to ambush whatever swam too close. Yet the teeth tell only part of the story. Elginurpaton's limbs, reconstructed from partial fossils, reveal heavy bones that were broader and more robust than those of earlier fish. They were not delicate paddles but sturdy supports, suggesting that the creature pushed itself through weeds or hauled across soft ground beside streams. Still, the joints were not flexible enough for walking in the way later tetrapods managed. It was caught in a halfway stage, powerful yet clumsy on land. The shoulder bones also revealed deep muscle attachments, showing that its forelimbs were strong enough to anchor the body as it heaved itself against the pull of water. This strength hints that Elginurpaton may have used sudden bursts of power to thrust forward, rather than relying on steady, rhythmic movement. The environment it lived in would have been a place of shifting opportunity. Late Devonian waterways were unstable, with rivers changing course and pools shrinking during dry seasons. A predator able to move from water to the bank, even awkwardly, gained access to new prey and new territory. Elginurpaton's body seems to have been shaped by this challenge, a response to a landscape that forced creatures to experiment with ways of surviving beyond the depth. Fossil evidence of its size adds to the drama. Elginurpaton is thought to have grown more than a meter long, making it one of the largest tetrapod-like animals of its time. A creature of that scale would have dominated shallow channels, its head breaking the surface as it lunged at fish. For smaller animals hiding in reeds, the appearance of such a predator meant the boundary between water and land was no longer safe. Despite its power, Elginurpaton's design carried limits. The limbs could brace and push, but the wrists and ankles lacked the range needed for steady strides. It could not march confidently onto dry banks. Instead, its movements were likely lunges, dragging its bulk forward in short bursts. This awkwardness shows that success outside water was not yet guaranteed. Evolution was testing possibilities, and in Elginurpaton the attempt was bold but imperfect. The unearthing of its fossils reminds us how incomplete our understanding remains. Unlike Ventostega, which left more complete remains, Elginurpaton survives in pieces that must be carefully interpreted. Paleontologists rebuild their image by comparing jawbones, limb fragments, and shoulder girdles to those of later tetrapods. Each comparison adds detail but also raises questions, reminding us that much of its life remains hidden in stone. What makes Elginurpaton remarkable is not that it represents a final stage in the journey to land, but that it embodies the uncertainty of the process. It was strong, predatory, and partially suited to land, yet it may have struggled to thrive beyond its watery borders. Its presence shows that evolution advanced not through a single successful leap, but through many trials, some leading forward, others ending in silence. Seen in this light, Elginurpaton becomes less a stepping stone and more an experiment, a path tested by nature, explored for a time, and then abandoned. Its bones, preserved in the rocks of Scotland, tell of ambition and failure, of an animal that pressed against the edges of possibility but did not fully cross them. As the Devonian world continued to shift, other creatures would carry the story onward, building on what Elginurpaton began, and from the shadows of its imperfect steps would rise forms that edged closer to a life truly on land. Acanthostega, the eight-fingered amphibian, across the quiet waters of Devonian swamps, towering plants cast shifting shadows and thin shafts of sunlight on the streams below. Beneath the surface, a creature swam with a shape unlike any fish and unlike any animal that would later walk on land. This was Acanthostega, and hidden in its paddling limbs was a clue that would reshape how scientists understood the first attempts at life beyond water. The most striking detail about Acanthostega is its hands. When its fossils were studied closely, paleontologists found something unexpected. Each limb carried not 5 digits, like modern amphibians or mammals, but 8. These digits looked more like broad paddles than fingers, spreading outward in a fan that was perfect for pushing against water. The discovery showed that the familiar pattern of 5 fingers had not yet appeared, and that early experiments with limb design were more varied than once imagined. The skeleton reveals a body still built for an aquatic world. Its ribs were short and unable to support much weight outside water, while its limbs, though strong, had joints that bent more like fins than legs. This means Acanthostega could not have carried itself confidently on land. Instead, the creature was adapted for swimming among plants, pulling itself through thickets of stems and leaves that crowded the ancient shallows. Its skull adds another layer to the mystery. Long and flat, it carried rows of sharp teeth suited for gripping slippery prey. The arrangement of bones around its ear suggests it could detect vibrations in water, helping it sense movement around it. With these tools, Acanthostega was well prepared for a world of lurking predators and quick ambushes, though not yet for the challenges of a dry shoreline. The story of its discovery began in Greenland during the 1980s, when paleontologist Jenny Clack and her team uncovered fossils that revealed the unusual anatomy. Until then, many scientists had assumed that limbs first evolved for walking on land. Acanthostega overturned that view. It showed that true limbs with digits appeared in animals that were still mostly aquatic, suggesting that fingers were not originally for walking, but for paddling and grasping in complex underwater environments. This insight changed how researchers thought about evolution's path. Instead of a straight march from water to land, the transition now appeared as a series of overlapping experiments. Acanthostega demonstrated that limbs did not suddenly appear at the shoreline, but were tested and refined in swamps and rivers, long before animals managed to leave the water. The 8 fingers were one of several trials, many of which would never be carried forward into later lineages. Its anatomy also speaks to how dangerous life was in those ancient waters. With predators like giant armored fish and early sharks nearby, maneuverability was essential. Acanthostega's broad digits and flexible joints gave it the ability to weave between underwater plants and escape larger hunters. Survival did not depend on walking onto land, but on using limbs to explore niches that fins alone could not reach. What makes Acanthostega so fascinating is that it embodies both success and limitation. It mastered its swampy home, thriving in tangled vegetation where more streamlined fish could not move. Yet its body was still bound to the water, unable to support itself in the open air. Its existence shows how evolution often moves sideways, testing new designs that do not immediately lead to dominance but lay groundwork for what comes next. The 8 fingers remain a symbol of this experiment. They remind us that what we see as natural and universal today was once only one possibility among many. 5 digits may have become the rule for later vertebrates, but Acanthostega shows that early amphibians explored different answers to the problem of limbs, each shaped by the pressures of their watery world. Even in its limitations, Acanthostega reveals the creative tension of evolution, where each adaptation opened doors to both opportunity and constraint. It could not walk across dry ground, but it proved that limbs with digits were useful long before land was conquered. And in its strange, 8-fingered form, we glimpse an evolutionary path that was left behind, yet still shaped the story of every creature that would one day step onto solid earth. Somewhere beyond Acanthostega's watery domain, other creatures were already preparing for the next step, and their designs would push the boundary between swimming and walking even further. Ichthyostega, the clumsy land explorer. The fossil of Ichthyostega tells a story written in bone and stone, a story of struggle at the edge of land. When first uncovered in Greenland in the 1932, its skeleton looked like something caught between 2 worlds, part fish, part amphibian, and not fully suited to either. Its frame hinted at one of the earliest true steps onto land, yet the impression it leaves is not of grace, but of awkward effort. What sets Ichthyostega apart is its spine and limbs. Unlike its close relatives, It had strong, overlapping ribs that created a barrel-shaped chest. These ribs could support more weight than those of earlier forms, allowing the body to resist collapse under gravity. Its forelimbs were stout and muscular, better at propping up the front of its body than at fluid swimming strokes. This anatomy suggests that while still tethered to water, Ichthyostega had the ability to push itself partly onto solid ground. The hind limbs, however, tell a different story. They were broad and paddle-like, less useful for walking and more suited to swimming. This mismatch between powerful forelimbs and clumsy hind limbs hints that Ichthyostega was no skilled land traveler. Instead, it may have dragged its heavy body forward in short, awkward movements, lifting itself only to flop down again. The ground was not yet its domain, but it was learning to test its possibilities. Its skull reveals further adaptations. The head was large, with strong jaws lined by sharp teeth, perfect for catching prey along the water's edge. A distinctive notch behind the skull may have helped with hearing and air, suggesting that Ichthyostega could detect sounds both above and below the surface. This dual sensitivity points to an animal exploring two environments at once, neither fully abandoned nor fully conquered. The Greenland fossils that revealed these details came from Devonian rocks more than 360 million years old. They preserved not just bones, but clues to the landscape in which Ichthyostega lived. Shallow lakes and river deltas stretched across the region, fringed by vegetation that offered shelter and new hunting grounds. In such settings, the ability to pull forward on mud or plants, even clumsily, may have meant survival when water levels dropped, or when predators prowled the shallows. For paleontologists, Ichthyostega marked an important step in understanding the transition to land. Before its discovery, the shift from fish to amphibian was imagined as a sudden leap, a single dramatic crossing of the shoreline. Ichthyostega showed otherwise. It demonstrated that the journey was piecemeal, filled with half-adapted bodies still tied to the water, yet edging into new worlds. Each bone of its skeleton carried evidence of compromise, a reminder that evolution works through trial and adjustment. The ribs stand out not just for strength, but for what they imply about breathing. A chest capable of resisting collapse also created room for the lungs to function in air. While Ichthyostega likely still relied on gills when young, its adult body shows greater preparation for drawing breath outside water. This blend of old and new features made it an amphibious pioneer, though still far from the agile creatures that would follow. What might daily life have looked like for this clumsy explorer? It may have hauled itself onto sandbanks to bask, resting its body in the warmth while keeping close to the safety of water. It could have hunted insects or small invertebrates near shore, snapping at them with quick lunges. Yet its heavy frame and ungainly steps meant it never roamed far, always returning to the refuge of its aquatic home. Land was an option, not a permanent place of belonging. Even its limitations are valuable to science. They remind us that the conquest of land was not a straight climb, but a staggered process filled with awkward beginnings. Ichthyostega did not stride across landscapes like later amphibians, but its experiments in movement opened pathways others would refine. In its half-successful steps, we glimpse the moment life began to imagine a future beyond water. From the muddy edges of its world, another generation of creatures was already preparing to take the venture further, building upon what Ichthyostega could only begin. Tularpeton, the six-toed, stepped forward. The first fossils of Tularpeton were unearthed on the Tula River near Arkhangelsk in northern Russia, and they looked strange even by Devonian standards. Among the broken bones was a forelimb with 6 toes, an unexpected count that challenged long-held ideas of how early tetrapods were built. Instead of the familiar 5-digit pattern that defines later vertebrates, this animal had an extra step in its evolutionary script, a reminder that the journey onto land was not yet settled into the rules we recognize today. Tularpeton lived roughly 365 million years ago, placing it among the last tetrapods of the Devonian period. By this time, Earth's shallow seas and river deltas were shifting, with climates that encouraged new adaptations. Unlike some earlier creatures still bound to water, Tularpeton showed signs of greater independence from its aquatic past. Its limbs were more advanced, jointed in a way that gave it stronger leverage, suggesting that it could manage short trips onto land without collapsing under its own weight. The 6-toed foot is more than a curiosity. It reflects a stage when evolutionary experimentation with body plans was still underway. Polydactyly, or having more than 5 digits, was once common among early tetrapods, but Tularpeton shows how diverse these patterns could be. Later lineages standardized the 5-digit design, but here we catch a glimpse of possibilities that were tried and left behind. It is a fossilized snapshot of variation before nature's blueprint narrowed. What also makes Tularpeton stand out is how much more terrestrial it may have been compared to its predecessors. The bones of its limbs were stronger and less paddle-like than those of animals such as Acanthostega or Ichthyostega. Instead of pushing itself awkwardly in mud, Tularpeton likely had the ability to lift and swing its body in a way closer to walking. This does not mean it was a confident land dweller, but it hints at a body better tuned to environments beyond the water's edge. The fossil record for Tularpeton is fragmentary, but what has been preserved is telling. Parts of its shoulder girdle and forelimb reveal joint surfaces that could withstand stresses different from those of swimming. Combined with its unusual toes, this anatomy paints a picture of an animal testing life outside the water more boldly than many of its ancestors. Each fossil fragment serves as a puzzle piece in reconstructing the uncertain steps of early terrestrial evolution. Its habitat likely included coastal shallows and river mouths, areas where tides and changing water levels demanded flexibility. In such places, being able to move onto damp ground or shallow sandbars would have provided access to food or safety from aquatic predators. Even a clumsy venture onto land could give advantages in reaching stranded fish or escaping lurking threats in deeper channels. The selective pressures of such environments may have pushed Tularpeton's anatomy towards stronger limbs and greater experimentation. The 6-toed limb also holds significance for the history of vertebrate development. It forces scientists to reconsider how digits formed and stabilized in the first place. Instead of being locked from the start, the number of digits was once fluid, shaped by trial and error. Tularpeton shows us that what seems inevitable in hindsight, the 5-fingered hand and foot, was not the only outcome. In this way, its fossils carry both biological and philosophical weight, reminding us that the structures we take for granted were once provisional. For researchers, Tularpeton bridges a gap. It lies beyond the more aquatic forms yet precedes the fully terrestrial amphibians of the Carboniferous. Its anatomy reveals a lineage stretching forward, pointing to creatures that would refine the ability to walk and breathe in open air. Even though the fossils are incomplete, the clues they give about musculature, joints, and digits make Tularpeton a critical marker of progress in this evolutionary march. The account of Tularpeton is less about victory and more about the shift from water to land. It did not dominate its world or establish a permanent lineage that survives today. Instead, it stands as a fleeting experiment, a short-lived branch on the evolutionary tree. Yet in its 6 toes and sturdier limbs, we see evidence of the restless search for new ways of living, a search that would eventually lead to the dominance of land vertebrates. From its unusual skeleton, the trail stretches forward to other pioneers, each carrying the legacy of these early steps and shaping the creatures that would one day master dry land. Hynerpeton, the muscle-powered walker. At Pennsylvania's Red Hill, scattered bones first whispered the presence of Hynerpeton, in a site that speaks richly of the Devonian world. Among the fragments were shoulder girdles so massive and robust that they immediately suggested a creature designed for powerful movement. Unlike other early tetrapods, which often left behind fragile remains, Hynerpeton revealed itself through strength, a fossil echo of an animal built to push against the weight of its own body on land. This creature lived around 360 million years ago, at the threshold between the Devonian and Carboniferous periods. Its world was one of swampy floodplains, river deltas, and lowland forests beginning to spread across the landscape. These environments were unstable, prone to shifting waters and dry spells, and creatures that could navigate both realms stood at an advantage. Hynerpeton's anatomy suggests it was among the first to make that shift, not with hesitation, but with force. The most striking feature of Hynerpeton lies in its shoulder and forelimb structure. The fossil bones of the shoulder girdle were unusually large, leaving space for muscle attachment, far greater than in earlier tetrapods. This indicates that its front limbs were not just for paddling or dragging, but were powered by muscle systems capable of lifting and propelling its body. Where earlier creatures struggled to haul themselves awkwardly, Hynerpeton seems to have developed the beginnings of a stride. Fossil evidence from Red Hill shows that Hynerpeton lived alongside lobe-finned fishes, early sharks, and primitive plants forming the edges of the first forests. In this mix, it occupied a niche that bridged water and land. Its muscular limbs likely allowed it to escape predators lurking in the shallows, as well as reach new food sources along the muddy banks. Each movement out of the water may have been clumsy compared to modern standards, but compared to its ancestors, Hynerpeton represented a leap forward in physical power. The name itself, Hynerpeton, reflects its origins. It comes from Hyner, the nearby town in Pennsylvania, combined with peton, meaning crawler. The name grounds the animal in its place of discovery, linking it to a small corner of Earth that once lay near the equator in a very different climate. At that time, Pennsylvania's landscape was warm and humid, covered with lush plant growth that created dense habitats where pioneering tetrapods could explore. What makes Hynerpeton remarkable is not only its strength, but what that strength represents in evolutionary terms. Strong shoulder muscles would have enabled it to push its chest upward, lifting its head to breathe air more easily when water levels fell. This motion, simple as it sounds, would have been revolutionary for survival in shallow, stagnant pools. Hynerpeton's body hints at a stage when breathing air and walking were no longer rare experiments, but skills becoming more reliable. The fragments of Hynerpeton also raise questions about its lifestyle. With only parts of its skeleton found, scientists cannot fully reconstruct its form, yet the evidence points to an animal less dependent on water than those that came before. Its four-limb power suggests it could drag itself over obstacles, maneuver along stream banks, and perhaps spend longer periods on land than most Devonian tetrapods dared. Each of these abilities would have opened doors to habitats closed to more aquatic relatives. Hynerpeton's discovery also highlights the importance of Red Hill as a fossil site. This location preserves a rare overlap of aquatic and terrestrial life from a critical period in Earth's history. Here, scientists can trace the mingling of fish and tetrapods, plants and invertebrates, all marking the transition from one era of life to another. Hynerpeton emerges from this mix as a symbol of the raw strength needed to push across ecological boundaries. While Hynerpeton itself did not give rise to modern animals, its anatomy shows a step in the larger pattern of innovation. Evolution was not a smooth climb but a branching path, where different experiments in body design were tested. Hynerpeton's reliance on muscle power demonstrates one of those experiments, the possibility of conquering land not through delicacy or chance, but through brute force. In the heavy bones of its shoulders, we glimpse the determination of life pressing forward, reshaping its body to seize new ground, and preparing for the creatures that would soon carry this momentum even further. Greerpeton, the long-bodied creeper. What immediately stands out about Greerpeton is its remarkable length. Unlike the short, stocky bodies of some other early tetrapods, this creature stretched out in an eel-like form. Its narrow body and extended tail suggest that it moved more like a swimmer than a walker, favoring stealth and agility in the water over brute strength on land. This unusual shape made it stand out as an evolutionary experiment, one that reveals how diverse the path from fish to tetrapod could be. In Nova Scotia, ancient rock layers cradled the fossils of Greerpeton, preserving its long, graceful frame. These remains date back to the early Carboniferous, a time when lush wetlands and swampy forests created a maze of shallow waterways. The environment was alive with insects, small fish, and amphibious creatures, making it a place where many body designs were tested by survival. The rocks that held Greerpeton's bones captured not just its skeleton, but a glimpse of the ecosystem it navigated. Some of these fossils even show traces of fine details, allowing scientists to reconstruct how its ribs and skull were arranged with surprising accuracy. Its elongated ribs hint at another layer of adaptation. They formed a cage that stiffened the body, preventing it from collapsing as it crept along stream beds. Unlike bulkier tetrapods that relied on powerful limbs, Greerpeton seemed better suited to hugging the ground and sliding through tight spaces. This rib-supported structure, combined with its long body, suggests it may have been an ambush hunter, lying low before darting forward with a sudden burst. The skull of Greerpeton adds to the picture of a specialized predator. It was flat, broad, and lined with sharp teeth, ideal for snapping at small prey in the water. The eyes, positioned near the top of the head, allowed it to lurk beneath the surface while still keeping watch above. In this way, it mirrored the behavior of modern crocodiles, using patience and camouflage as its main strategies. This subtlety of design shows that not all evolutionary steps were about marching onto land. Some were about mastering the waters in new ways. Breathing was another key factor in its life. Evidence suggests that Greerpeton may have retained internal gills, but also had lungs, giving it a dual system. Such a setup would have been useful in the swampy waters of its time, where oxygen levels could vary wildly. If a stagnant pool lost its air, Greerpeton could rise and gulp from above, while still depending on gills when submerged. This dual ability was not just survival insurance, but a clue to how respiratory systems shifted during the march toward land. This dual system may have allowed it to remain active in waters where many other animals would have struggled, giving it an edge in hunting during low oxygen conditions. The limbs, though present, were not strong enough to carry it far across solid ground. They likely served as stabilizers, paddling along the bottom or bracing against rocks while swimming. In this sense, Greerpeton was not aiming to conquer dry land, but was shaping a lifestyle that blurred the boundary between fish-like and amphibian life. Its form was less about dramatic leaps forward and more about refining a way of survival that had worked for millions of years. The true fascination of Greerpeton lies in its lesson. Evolution is not a straight line, but a web of possibilities. While some relatives were testing stronger limbs or new walking patterns, Greerpeton was showing that long bodies and stealthy swimming could also carve out success. The diversity of approaches at this stage highlights the trial and error nature of life's story, where no single solution was guaranteed to dominate. Instead, different creatures carried different pieces of the puzzle. Its place in the fossil record reminds us that the journey from water to land was never simple. Greerpeton was not a failure, nor a direct ancestor of modern animals, but one of many branches exploring possible futures. Its slender shape, quiet movements, and adaptive breathing all speak to a world in flux, where creatures were pressed to innovate in countless directions. This small, creeping figure tells us that the transition was not a march, but a tangle of paths, some ending, some continuing, and some vanishing into shadow. Beyond Greerpeton's still waterways, other creatures were stirring, ready to attempt the next bold chapter in life's unfolding tale. Wachiria, the crocodile-like predator. In the early 1990s, a limestone quarry near the small town of Wachir, Iowa revealed a set of ancient bones unlike anything seen before. The fragments were scattered and worn, but they carried the unmistakable outline of a large early tetrapod. From those stones emerged the name Wachiria, honoring both the town and the animal whose remains had been hidden there for over 330 million years. It was not a fragile creature or a quiet experiment in land living. This was something stronger, heavier, and more fearsome than many of the pioneers that came before. When scientists pieced together the fossil, they saw a predator built for force. Its skull stretched nearly half a meter long, narrow at the snout but broad across the back, with deep grooves where powerful jaw muscles once attached. The teeth were sharp, recurved, and closely spaced, forming a trap that could pierce slippery prey and hold it fast. Compared to earlier tetrapods with more delicate heads, Wachiria looked almost crocodilian, though it lived long before any reptile had appeared. Its face alone suggested an animal that relied on speed and crushing power. Imagining this creature by the banks of an ancient stream paints a vivid scene. With its long body partially submerged, it may have waited in silence for fish or amphibians to swim too close. Then, in a sudden burst, the jaws snapped shut, pulling the victim into deeper water where escape was impossible. Few early tetrapods give such a clear impression of predation. Where others appear tentative, Wachiria looks decisive, as if life on land and water was not an uncertain trial, but an opportunity for dominance. The bones themselves tell much about its strength. Fossilized ribs show that the animal had a reinforced chest, capable of supporting heavy muscles and protecting large lungs. Its limbs, while still splayed to the sides, were sturdier than those of many predecessors. This did not mean graceful walking on land, but it did allow short, forceful pushes, letting the animal drag its weight across mud or lunge forward in bursts. Combined with its size, estimated at around 2 meters long, Wachiria was among the largest predators of its age. The aspect that sets this discovery apart is its timing. Around 340 million years ago, the ecosystems of North America and Europe were filled with small tetrapods that struggled at the edge of water and land. Most were modest in size, vulnerable to larger fish that still ruled rivers and lakes. Into this setting appeared Watcheria, not as prey but as hunter. Its body plan suggests an evolutionary leap toward using strength and aggression to carve out a secure role in a changing world. It was no longer enough to adapt quietly. Survival now also depended on who could overpower whom. The quarry where Watcheria was found has become a window into this dangerous landscape. The layers of limestone preserve not just bones but impressions of ancient habitats, from shallow streams to swampy lowlands. Fossils of other animals found alongside Watcheria reveal a community of fish, amphibians, and early invertebrates, most of which would have been potential prey. By placing the predator among these remains, researchers can picture an ecosystem where, for the first time, tetrapods were beginning to hold the top positions in the food chain. Yet for all its power, Watcheria was not invincible. Its sprawling posture limited its speed on land, forcing it to stay close to water for protection and movement. The jaws were built for grabbing and holding, not slicing, so prey had to be swallowed whole. These limits show that even the strongest of the early tetrapods remained tied to the water's edge. Still, its existence proved that land was no longer a place visited only by fragile bodies. It could now host predators capable of shaping entire environments. The journey of Watcheria is equally a journey of scientific patience. The fossils were first uncovered decades ago, but only through careful preparation and study did their importance become clear. Each bone added a piece to the picture of an animal that combined the body of an amphibian with the ferocity of a crocodile. The name chosen, echoing the Iowa town of Watcheria, now carries global significance as one of the key markers of early tetrapod evolution. What Watcheria leaves behind is a sense of danger entering the evolutionary record. It was not only about exploring the shoreline anymore. It was about ruling it, with jaws built for crushing, lungs capable of sustaining lunges, and limbs strong enough to anchor a strike. This creature stood as proof that the new world beyond water could also be claimed by power. In the world beyond its crushing bite, new adaptations were taking shape, ready to tip the balance once again. Pederpes, the first true land stepper. The wind swept across the rugged hills of Devonian Scotland, carrying a hint of ancient rivers long vanished. In the early 1970s, a fossil emerged from the muddy rock, catching the attention of paleontologists who sensed it was unlike anything seen before. This was Pederpes, an animal that didn't just dabble on the edges of water but truly stepped onto the land, opening a new chapter in the story of life. Its body tells a tale of movement and exploration. Unlike creatures that clung to shallow waters, Pederpes had limbs positioned beneath its body, allowing it to lift itself fully off the ground. Imagine it maneuvering through thick mud and fallen plant debris, each step carefully balanced, each stride deliberate. Its feet were broad and strong, sculpted to grip the terrain rather than push against water. In these adaptations, the earliest experiments in true land locomotion can be glimpsed. Examination of the fossil reveals that Pederpes had a surprisingly flexible neck, allowing it to survey its surroundings without moving its whole body. This feature would have been crucial for spotting prey or predators while navigating unfamiliar terrain, giving it an early advantage over less agile tetrapods. Neck mobility hints at a growing independence from water, as the animal could survey and interact with the land environment in ways earlier species could not. The skull hints at a life lived in alertness. Eyes faced forward, scanning the surroundings for both prey and danger. The narrow jaw suggests it fed on small fish and invertebrates, but the real advantage came from its ability to hunt across mudflats and shallow pools, venturing further than any semi-aquatic ancestor. For Pederpes, the land itself became a hunting ground, full of untapped opportunity. Its breathing apparatus had evolved to match this new lifestyle. The ribcage, curved and reinforced, supported lungs capable of sustaining movement away from water. Unlike earlier tetrapods that gasped at the margins of ponds, Pederpes could draw deep breaths while trekking across uneven land, making the air itself a new resource for survival. The environment was as challenging as it was unfamiliar. Scotland's Devonian wetlands stretched wide, punctuated with streams and ponds. Fallen plants in shallow waters formed obstacles that required coordination and control. Its short tail and muscular legs helped maintain stability, hinting at the delicate art of walking on mud and rock, rather than swimming through currents. Subtle details in the vertebrae suggest that Pederpes could support bursts of speed, possibly to escape sudden threats or to chase quick prey. The spine shows evidence of strong muscle attachments, indicating a powerful, coordinated gait. These adaptations reveal that life on land was not merely a slow, cautious process. It demanded agility and energy management, which Pederpes was beginning to master. Even the joints of its ankles and hips reveal a remarkable flexibility. This creature could twist and adjust its steps, stepping around obstacles that would stop less adapted tetrapods. Each movement was a small triumph over gravity and terrain, a quiet demonstration of evolution's ingenuity. The discovery itself was a story of persistence. Geologists and paleontologists had sifted through layers of rock, following subtle clues embedded in stone. When the fossil finally revealed its secrets, it became clear that vertebrates had already begun mastering land in ways far more sophisticated than previously thought. Pederpes wasn't just surviving outside water, it was thriving. Chemical analysis of the surrounding rock layers shows that this region experienced periodic flooding and drought, creating a challenging and dynamic environment. Such conditions would have selected for resilience and versatility, favoring animals like Pederpes that could move between water and land as needed. Its lifestyle likely involved both hunting in shallow streams and exploring mudflats, making it a true pioneer in exploiting mixed habitats. Its footprints, faint impressions in ancient mud, provide another window into its life. Unlike clumsy tracks of semi-aquatic tetrapods, these prints show alternating steps with clear toe marks. They speak of rhythm, coordination, and the first real mastery of walking. These prints mark the moment life fully embraced the land, leaving traces that would inspire countless evolutionary chapters to come. The very existence of Pederpes challenges assumptions about the pace of adaptation. For millions of years, tetrapods had been tentative on land. Yet here was a species already refined, perfectly poised for terrestrial life. Every movement hints at a future where forests, predators, and terrestrial ecosystems would flourish, rooted in these first careful steps. In stepping across the Devonian landscape, Pederpes became a pioneer, and its journey whispers of a world that life was only beginning to claim.